Okay, and to finish off our discussion of differential equations, let's spend just a bit of time talking about some applications. So I think we've already spoken about one of the applications of differential equations. How that rhymes. Does it rhyme? Assonnates? I'm not sure. I think the most obvious one is finding an expression for y given initial conditions. Okay, and we've done a bunch of these already, but here's this next one. So have a go at part question A and question B, and then yes, we can discuss. So let's do part A. I'm assuming you've paused and had a go. So it says find the values of B and C so that this is a solution to this. So I think we should probably just take the derivative and see what happens. So y dash equals 3e to the 3x plus b. It seems like they've replaced the e to the 3x with y minus bx minus c. Like this. And then minus 4 plus b. Cleaning this up, we get 3y minus 3bx minus 3c plus b. Okay. Now, if this is supposed to equal 3y minus 18x, then this minus 18 should correspond with this minus 3b. So therefore 18 equals 3b, and therefore b equals 6. And then the fact that there is a no constant on this side means that this constant should correspond with this. We can say 0 equals minus 3c plus b, 3c equals 6, and c equals 2, because b equals 6. Perfect. That's part A. Pretty chill, no dramas. Find, and so that is a solution to this second order differential. Okay, so it seems like we have to take the first and second derivative. So the first derivative is, if I'm whispering, I hope it doesn't come out bad. Just that I think everyone else is asleep. It's 1 in the morning, so maybe that's why. Okay, taking the derivative, we get minus 10n sine nx. That's atrocious. Let me fix this up. And taking the second derivative, we get minus 10n squared cos nx. And we have to compare this with minus 49y. Oh, okay. I think you can see that y equaled 10 cos nx. So if we just rewrite this a bit differently, let's write this as minus n squared 10 cos nx. I don't really need that. And this becomes minus n squared y. Now you can compare this with the minus 49y and say, oh, clearly n equals plus or minus 7. Not bad, right? Not bad. Perfect. So that's just normal, no real physical applications of differential equations. Let's now talk about some physical applications. What we're going to talk about here is this thing called the logistic equation. You don't need to kind of stress yourself out over this. Basically, logistic equations, like the general definition, is that they somehow model the population of something with respect to time. A logistic equation is the differential form of that model. Okay, I think we dealt with an easy example of this back in year 11, exponential growth and decay. So exponential growth and decay is a simplified version where actually, how can we say, let's say the population of something was given by a e to the kt plus b, where a, k, and b are constants. Okay, and depending if k was positive, it'd be growth. If k was negative, it'd be decay. Perfect. And I think the derivative, we had a form for the differential. The differential was given by dp on dt is given by k n minus b, something like this. P minus b, sorry, getting my equations confused. P minus b. Perfect. Anyway, and we could have solved those questions. Usually in year 11, we had to be told this, or we had to have learned this and memorized it. But now that we know differentials, you can actually go from something like this back up to something like this anyway. So it's not a big deal. But that's the easy version. There's this thing called logistic growth, or we even have logistic decay, where instead of just going directly exponential, like exponentially increasing, exponentially decreasing, it actually starts off a bit slower. It has a small rate of change at the beginning, which you can sort of see here, and then it increases, and then it decreases back again and approaches some asymptote. Okay, so that's this little extra complexity to it. Okay, do I have any point to make about this? Oh yeah, this is something that we'll be dealing with. The logistic equation, the differential, will actually give it, I think I'm using n's for this, dn on dt equals, and it's kn p minus n. Okay, so n is the variable which could represent the population. K is whether it's increasing or decreasing, and p represents the, I guess, like the asymptotic population. What it's going to approach as n goes to infinity, so the limit. Perfect. Now, to solve this, actually, I'll get you to solve something like this first, and then we'll come back to that. So I want you to have a go at solving this question here. Coming up with a differential equation, and then once you come up with a differential, being able to go back up and find all, part A and part B. Nice. Pause and unpause. So let's have a go now. The rabbits on Bandicoot Island are increasing. 50 years ago, 100 rabbits were released, and now there are 10,000 rabbits. Assume in this example that the rate of increase of rabbits is proportional to the number of rabbits. Find the equation at time t years after they were introduced, and then part B and C. Nice. So we've got to come up with a formula for part A first. A, it says the rate of increase is proportional to the number of rabbits. So that means dn on dt equals k, the constant of proportionality, to the number of rabbits, to n. Okay, so k is a constant of proportionality. Proportionality. Proport, whatever. Okay. Now, let's solve. So I think if you want to solve this equation using our differential forms, the n represents sort of like the y's in all of the equations before, and t is like the x in the equations before. So I'm thinking making this 1 on n dn dt equals k, and then integrating both sides with respect to t. And this becomes dn equals, and then the integral of k dt. K is a constant, so that's fine. The integral of 1 on n dn is ln of the absolute of n, and this is kt plus c. now integrate, or let us rewrite this as as n equals e to the kt plus c, which also means a e to the kt, because e to the c is just a constant. We can write that as a. Lovely, lovely. Perfect. So we did this. Now we have to try and find a and k. So it says 50 years ago, bit confused. What do you mean by 50 years ago? Okay. So are we going to make time? Oh, at 50 years ago, they were released. Okay, makes sense, makes sense. So that refers to time equals 0. So at t equals 0, n equaled 100, because I think they released 100 then. So 100 equals a e to the power of 0, which means a equals 100. Nice. So therefore, n equals 100 e to the power of kt. And what have we told later? And now there are 10,000 rabbits. So at t equals 50. Wait, 10,000? Yeah. So 10,000 equals 100 e to the power of 50k. Divide both sides by 100. I think we get 100 here. And taking the limit both sides, defining both sides by 50. There we go. So therefore, n is given by 100 e to the power, so 100, yeah. K. We put the t there. There we go. That's our equation. Not bad, right? Yeah, not bad. Now part B, part 1. So let's find how many rabbits there will be in another 25 years and another 50 years. I mean, we'd have to do this. You just sub in t equals 25 and t equals 50. I think they both come out to be kind of neat numbers because I believe the logs cancel. Yes, I think you get like 1,000, and I'm not sure, but yeah, whatever. We get the idea. 1,010. Who knows? No, you don't get 1,000. Sorry, but whatever. I'm not doing this. So that was the easy version of these questions. But now that we try and solve questions with this new logistic equation, we run into some issues. So let me rewrite that equation from before. So logistic equation. Actually, you know what I'll do for this, just so I feel like I don't. In another 25 years, you let t equal 75, and here you let t equal 100. As long as you did that, then you should be good. So the logistic equation was given by this, k n p minus n. Now, if you try and solve this, you're going to run into a bit of an issue because you have to divide both sides by n p minus n. Remember, p is just a constant, and this becomes 1 over n p minus n dn on dt equals k. And when you go to integrate this with respect to t on both sides, you run into an issue on the left-hand side. Particularly not knowing how to integrate this, okay? There's no real direct way for you to do it. The way that you have to do it is by using a 4-unit method called partial decomposition or partial fractions, okay? you're not going to get taught this. So instead, what's going to happen is they're going to ask you a part A. They're going to ask you first to prove something, then you can use that proof in actually being able to calculate, being able to take the integral. Okay. So what I'll do, I don't want to sort of throw you off with this. Actually, no. I'll chuck in this question. We can do it. Okay, so here we have it. It is estimated the maximum carrying capacity of the Bandicoot Island. Oh, Bandicoot, like Crash Bandicoot. Oh my gosh, I remember playing that back in the day. Anyway, it's 20,000 rabbits. Use population values in the previous worked example, but model population growth using the logistic equation. So I think that was just saying that t equals 0, the population equaled, what was it, 100, and t equals 50. Oops, I should not use p. N equaled 100, and t equaled 50, n equaled 10,000. Nice. Okay, so it's given by this. I don't see how it says dn on dt equals this, where p is 20,000, where p equals 20,000 is the maximum population. I don't think we need to be given that. As soon as it says the maximum carrying capacity is 20,000 rabbits, that's going to be the limit. That's going to be what it's going to approach. So we automatically can tell that's going to be the p. Okay. So it says prove part A, the partial fraction decomposition that. So how are you going to prove this partial fraction decomposition? Okay. I think we're going to start with the right-hand side. So in 4-unit, they'd have to show this themselves. Whereas here, part A is always going to be, they give it to you, you just have to sort of prove right-hand side to left-hand side. Okay. Now I think we can make a common denominator. So p minus n, p minus n, p, p. So we get p minus n plus p over, and then we get n. Wait, times by n. What am I doing? Baboonery over here. Anyway, these cancel, and then this p cancels with that. So we did part A. Now we can use this for part B. So it says find the equation of the population after a time t is after introduction. So we're going to take our equation, which is dn on dt equals k n p minus n. Let me confirm that I've written that correctly. And we'll do what we normally do. Let's separate it and take the n times p minus n onto the other side. Actually, we don't even have to do that. Let's just take the reciprocal. The t on dn equals 1 on, and then, oh well, yeah, this is way easier than moving it over for no reason. and then that means dt, dn, dn, dt is going to equal, I'll take that one on k out because it's just a constant. The other ones have n's in them, so I can't. Now this is where we use part one. So for part one, we showed that it ends up being this thingy here. So let's just copy that in. My left-hand side, the integral of nothing of 1 dt is just t. That's 1 on k times okay, this is kind of scuffed, but integrate this dn. Wonderful. Again, the p is a constant, so let me just take that out. pk integral of 1 on n plus 1 on p minus n. Now you can tell that this is just logs. Ln of n, and then minus, and you can show this yourself if you're not convinced of my working, plus c. And then this is
okay, and let's make n the subject. So multiplying everything by pk, we're going to get pkt equals ln of n on p minus n. And then because c is a constant, if you multiply it by two other constants, it's just going to make a new constant, isn't it? So I don't have to worry about it anymore. Like whatever, like I'm still going to evaluate some constant, and who cares if I don't need to break it up. And taking the c over to the other side, we have pkt minus c equals ln of this, and putting it into exponential form. Okay. I'm just going to split this up into e to the pkt times e to the minus c. Then e to the minus c is just a new constant anyway. So I guess that can just become a. Okay, multiplying both sides by p minus n. And we're trying to get n as a subject, so we still got a bit of work to do. So we're going to have a p e to the pkt minus n a e to the pkt equals n. Moving this to the other side, we get n plus n a e to the pkt equals ap e to the pkt. Let's factor out an n. And do we have much more to go? I don't think so. I think we're almost there. Okay, so I guess you can leave it in this form, but this form is, I don't know, I don't like the fact that there's two exponentials. Usually this particular type of exponential growth / decay is really in a different form where there's only one exponential function. And it's even better for taking limits. So we'll talk about this in a moment. So what I'll do is I'm going to divide everything by a e to the pkt. As long as I'm dividing every term by that, it's not changing the value of anything. It's not like I'm affecting the fraction. So then this is going to be p over. Now we have e to the minus pkt. That's this thing. But 1 on a is a constant anyway. So 1 on a is just a new constant. So I may as well just write it as like a b, and then plus 1. And there you go. This is our exponential form. So that's that. Now I think we need to be able to find the values of b and k. We already know what p is. So what was it? At t equals 0, n equaled 100. So 100 equaled, p was 20,000. They gave that to us in the question. B, e to the power of 0 is just gone, so it's just b plus 1. And that means b plus 1 equals 20,000 over 100, so 200. And therefore b equals 199. Nice. And then what do we know? At t equals 0, no, sorry, at t equals, what was it, 50? Yep, n equals 10,000. So now, 10,000 equals 20,000 over and then this is going to be minus pkt. I'm just going to leave this as that because I don't want to keep writing everything in at once. It's going to get way too ugly. Dividing or swapping the fraction, the denominators, you get 199 e to the minus pkt. And then equals 2. And then moving that over, we get 1. Then we divide by 199. And we get e to the minus pkt equals 1 over 199. And that means minus pkt equals ln of 1 on 199, which is minus ln of 199. And then therefore, whoopsie, k equals, negatives cancel, 1 over pt ln of 199. And then we know what p and t were. I think this was at t equals 50 and p equals 20,000. So 50 times 20,000 is 1,000,000. So 1 10 to the power of 6. Very nice. There you go. So therefore, when you write your final answer, I think it's best to write like this: p over b e to the power of minus pkt plus 1, where p equals 20,000, b equals 199, and k equals 1 over 10 to the 6, which is 1,000,000, because we've got 6 zeros, ln of 199. I think that's the best way to do it because you don't want to bombard this equation with all of these constants. Okay. Yeah, so that's generally how you sort of get to a logistic equation. And then from here, we can just answer a few questions. So find how many rabbits there will be in another 25 years and then 50 years. So I guess you just go to this and you sub in. So this is probably C part 1. let t equal 75, and then let t equal 100. Okay, and then just chuck that into your calculator. You should be rounding down because you wouldn't have reached the next rabbit or whatever it is. Okay, so make sure you consider that. Yeah, I guess that's that. What I'll get you to do is just practice this, excluding all of the, I guess, the context. I'll get you to just practice doing this sort of question, right? Like doing the integration part, because I think that's the trickiest. Okay, so have a go. And yeah, all right, Matt. Now I'll show you how to do this as well. So it's very similar to the logistic equation from before, except here we don't have all the context. We're just practicing our integration. Yeah, our integration skills, or our solving differential equation skills. So show that that's the case. Oh, I have to do this. Nice. So that's part A. And then part B. Solve this, giving your answer as an equation for t in terms of x. Nice. So we have to integrate it. But I can't just integrate it with respect to time because I have x's on this side. So let me take the reciprocal. And now I can integrate with respect to x. Those cancel. This just becomes the integral of 1 dt, which is t. And then now this, because I can't do anything with it directly, I can then go and split it up to be 1 on x minus 1 on x plus 1 dx, like this. Like that. And let's move this over, t minus c equals, and then bring this all together. And let's put this into exponential form. So x on, what does it say? For t, in terms of it, oh wait, no need. Oh, I think we're done. For t in terms of x. Okay, I guess we did it. But let's just chuck in the next part because I feel like that was way too easy. I'll say plus 4x in terms of t. So now we need to get x as the subject. So t minus, I should do this in red just to show that it's the next part. And then x on x plus 1 equals e to the power of t minus c. Again, that e to the minus t can be written as a. Multiplying both sides by x, we get ax e to the t plus a e to the t. Moving that over, we get x minus ax e to the t equals a e to the t. Taking out an x, and dividing. Okay, and just for this to make it a bit neater, let's take this, move that down a bit, and divide every term by a e to the t. That becomes 1 over, and then 1 on a just becomes a new constant b, and it's e to the minus t minus 1. There you go. Not bad. So that's how you do this. Do I have any other points to make? Not really. Like, there are difficult questions out there. Okay. Particularly with, I mean, this is sort of like everything, right? The hard questions are the physical applications. So we'll go through more together in class. Maybe they don't have to be logistic equations, or they don't have to be equations about the population. They could be about the salt levels in a tank or something. Okay. But we'll go through those difficult ones in a class once you get a bit more of a hang of the easier ones. Okay. I think I'll end it there. All right, bye.